Good afternoon. I'm really glad to be here today to talk about the diet, so how we provide the energy that was mentioned yesterday. And I'm going to talk about the Isotope Studies, like what they taught us about ancient diets. But I'm not going to do a review of the literature. I'm more going to talk about what are the limits now, like what are the questions we cannot answer with the isotopes and why, and what could be the solutions. But I wanted to start with a simple question. So why do we care about diet? So there is obviously like this question of we have to provide energy to the body that was mentioned yesterday, but it also impacts the lifestyle in terms of the technology, the mobility, or even the densities of the population. Also, the health and the biology. So for this, we can give the example of the lactose intolerance. Like the first Neolithic farmers were apparently intolerant to lactose, but then there was a mutation where people could start to drink milk, and apparently it has been selected. So it's this link between like the diet and positive selection. Of course, it also reveals how hominins exploited their environment, and something that has been mentioned yesterday, this link with even the human evolution, with the expansive tissue hypothesis, where I can maybe just mention it again. The idea is that the increased meat consumption in human evolution could have allowed the development of the volume of the brain, because basically if you have a smaller digestive tract, then you have more energy for the brain. And now, okay, so we know why we care about diet, and the question can be how to know past diets. So I made a list of methods that can indicate what ancient hominins were eating. It's not exhaustive, but oops, sorry, yeah, here. So what we could mention is, of course, when it's recent, but still, we can have the art or even the historical writings. We can have the artifacts, the zooarchaeology, like depending on the animal remains that are on the archaeological sites, and if there are cut marks or not, we can know what were the species that were hunted. And so the dental calculus that can have some micro remains of plants, or even like DNA of plants, bacteria, and so on. The wear of the teeth can tell you what was eaten, and the isotopes. And so why am I particularly interested in the isotopes is because they will give another approach to the understanding of the diet. It won't be like presence-absence of a consumption. It would be more in terms of frequency, like how important was the meat, how important were the plants, and so on, which is then interesting to answer those questions about the link between diet and human evolution. Like, was the meat so important in the diet of a Neanderthal or Australopithecus? So what kind of isotope studies we can do and how? So, of course, we do it on human remains. And so you have in the bone two fractions, the collagen, which is the organic part, around 30%. So it's the proteins of the bones. And the bioapatite, which is the mineral part of the bone. And the collagen, because it's made of protein, it contains a lot of carbon and nitrogen. They are the main elements. And the bioapatite can also contain a bit of carbon. And so these elements, they so like in the body, nitrogen or carbon can have several what we will call isotopes. So the atom can be heavy or light. So the atoms of carbon, for example, will be heavy if there's more nutrients and the lights less nutrients. But all of these atoms of carbon have the same number of protons. They are isotopes. So usually people know the radioactive isotopes, like the carbon-14. that has a core that's unstable and then will decay over time. But today we're going to talk only about the stable isotopes. And so as I mentioned, some are heavy, some are light, and their proportion won't vary over time. So when someone will die, the proportion of heavy and light will stay the same until we analyze the ratios in the laboratory. And we can measure the proportion of heavy and light isotopes with this equation that gives the delta notation. And it can tell us what people were eating, because some food products are rich in heavy isotopes and some are poor. So how does it work? So you can do this delta notation for carbon and nitrogen and for all the elements, but I'm going to talk about these two first. And so I mentioned that some food products are rich in heavy carbon isotopes. And this is the case in marine environments, where you can see the values are higher. It indicates more heavy isotopes. So in marine environment, the values are higher than in terrestrial environment for carbon. And for nitrogen, it works differently. It's not depending on if it's marine or terrestrial. It mostly depends on the trophic level, so the position on the food web. So the carnivores will have more elevated values than the herbivores. And so then you can measure these two isotope composition and estimate where were the ancient hominins, humans, or animals in the food webs, and so what they were eating. And so if you look at Neanderthals and modern humans, usually it's what you see. Of course, there's variation between sites. But it would be the Neanderthals are slightly above the other carnivores, and humans are even higher, and for the carbon, they can be quite variable. So how to interpret this? The common interpretation is, you can see again this time carbon and nitrogen just for Neanderthals with these little squares, and the circles are modern humans. And usually you can see again, so the humans are higher for nitrogen, and for carbon it can vary. And the interpretation is usually modern humans are also eating fish, which freshwater fish, that's why the carbon is not so different from the Neanderthals. But that's why the nitrogen is higher, because there's more trophic levels in marine food webs. And so the nitrogen values when you eat fish tend to increase a lot. And the Neanderthals would be just top carnivores and possibly eating mammoths that usually have also higher nitrogen isotope ratios. But recently there was a lot of discussion about the interpretation of those diets, because there's actually many reasons why nitrogen isotope values could be high in the collagen. It could be related to, as we said, they just don't eat plants, they eat fish, but also, like I was just saying, they eat mammoth because they have nitrogen values that are equivalent to the trophic level of carnivores sometimes. They can be still breastfeeding, or they can eat animals that are still suckling, because basically, on the isotope point of view, a baby will eat his mother or her mother, and then you are one trophic level above. And so that's the same for the animals. It could be also, as Jean-Jacques mentioned it, like the consumption of putrid meat. Like the putrefaction is supposed also to increase the nitrogen isotope ratios in the meat. Mushroom consumption has been suggested. Cooking could also have an impact, like sometimes it appears that it would also increase the nitrogen, sometimes not, so it's discussed. The carnivore, like just on a theoretical point of view, it could be possible too, because they have elevated nitrogen isotopes values, and also the environment. And that has been suggested recently to explain the difference between the Neanderthals and the modern humans, because basically depending on the aridity, humidity, and so on, you can have a change of the local nitrogen isotope values that will impact the whole food web. And what happens is that most of the Neanderthals that have been analyzed for carbon and nitrogen They are from a Middle Paleolithic context, whereas the monuments from Upper Paleolithic context, so it could be just a change of environment during those time periods. And another problem is that recently we noticed a pattern that was not the common pattern observed for Neanderthals and monuments. So I have here all the sites where you have at the same time ancient hominin and the associated fauna. So this is, you have the little crosses that are the monuments and the square are Neanderthals. And so, like, when you go up, you can see, like, more and more elevated nitrogen isotope values. And so what we recently, so the common thing is to see that the monuments are more elevated than the local carnivores that are in red. So you have this here, here, or here in Buankaya very clearly. And that the Neanderthals are just a bit higher than the local carnivores. So this is true here. But recently, on two sites, Les Côtés and Grotte du Rennes, we observed at the Max Planck Institute that the Neanderthals were much higher than normal and were having values that are comparable to the values usually observed for modern humans. So can we still explain their diet with just only carnivore, like just as a carnivore, terrestrial carnivore diet? And another problem is, that the fact that they were not eating plants or only almost not eating plants is now discussed because of the analysis that have been performed in the dental calculus, where you can find a lot of micro remains of plants, and also, like, I think from the micro DNA point of view, you can also see it. So there's definitely some plant consumption, to which extent, this is a question, but like the interpretation of a top-level carnivore diet is not that clear. So what can we do? We can go back to the collagen, and instead of working on the bulk collagen, work on the different amino acids of the collagen. So the collagen is a protein, and like all the protein is made of different amino acids that are like smaller molecules, and you can analyze the isotope ratio in these amino acids separately, and so get the nitrogen isotope values for each amino acid, and the same for carbon isotope values. And why is it interesting? So here you have a graph with the nitrogen isotope composition of the phenylalanine and the glutamate, and then you can see so you can see that these values will be only impacted by environmental factors and not the trophic level, whereas this one is also impacted by environmental factors. That's why the values will correlate on a line. When you analyze like a lot of plants, they will fall in this line because both values will correlate. But this one is also impacted by the trophic level, the position in the food web, which means that if you have like one plant here and one animal that will eat it, it will be one trophic level, so on this line. So basically, if you use the two isotope composition, you will have all the plants on this line, all the herbivores on this line, and all the carnivores here, whatever the environment is. So we can interpret the nitrogen isotopes without having interferences of the environment. And so it has been performed for 4 hominins, so 3 like Paleolithic hominins, 3 Neanderthals, and 1 monohuman. And so you can see the results here, like for 4 sites, I should say. So this is for the site of SPI, and then you can see all the herbivores that are falling on the trophic level line that corresponds to herbivores, so perfect, including the Neanderthals that have the highest value for both amino acids, and which explain why also the values are elevated when you consider the whole collagen. And the Neanderthals are falling under the line of the carnivores, so it would be around 20% of plants. So using this method, we can estimate this kind of thing. Now it has been done also for the modern humans from Burankaya, and they were having the most elevated nitrogen isotope values ever seen in a Paleolithic context. And so you can see again the herbivores here, one wolf on the line of the carnivore, and here all the foxes and the modern humans. And so basically you can see that again the modern humans are under the terrestrial carnivore line. So you don't even need fish to explain why the values are elevated. It could be just due to environmental factors. And now we also have the two Neanderthals from Les Côtés and Grotte du Renne. So Grotte du Renne, it's a baby. And so that could explain why the values are so elevated just by breastfeeding. And when you look at the values, like this baby has also a trophic level above the terrestrial carnivore, which is compatible with the hypothesis of breastfeeding baby. And for the site of Les Côtés, this time we have an adult, and this adult is falling on the carnivore line, almost. So in this case, it would be like more traditional interpretation, carnivore diet, even though they are the most elevated values also for nitrogen ever seen in Neanderthals. Now, what can we do when we don't have collagen? We can still analyze, because the collagen is a protein that will disappear after some time, like it cannot be preserved because it's organic matter. But we can still work on the mineral part of bones or teeth. And we lose the nitrogen, but we still have the carbon. And it has been, so we can do it also on enamel that's resistant to soil contamination. And it has been done a lot in African context, because you will have differences for the carbon isotope values between the trees that have a C3 metabolism for the plants and the grasses that have a C4 metabolism. So this C3, C4 is just when there's the photosynthesis, the first molecule to form for C3 will have 3 atoms of carbon, and for the grasses, they will have 4. So usually, yeah, and it will impact the isotope values. So basically, the trees will have lower isotope ratio for carbon, and the grasses most elevated values. And so it has been used to interpret if ancient hominins were evolving in an environment where you had a lot of trees or a lot of grasses, so forest or savanna. And so it has been like Sponheimer and Julia Littorp that work a lot on this, and Tjoserling. And they work on different Australopithecus, Paranthropus, early Homo, and what they see is that the values don't depend on the taxonomy, if it's an Australopithecus or Paranthropus, but more over time you will see progressively values that will correspond to the savanna, whereas when you look at ancient times it would be more like a forest environment. The problem is that this doesn't work in a European context because the trees are C3 and the grasses as well. So you don't have access to this kind of values. And the other problem when you work on the dental enamel is that you don't have access to the trophic level. So what's the solution? There is now a new type of isotope analysis that are becoming more and more common in archaeology. It's the non-traditional stable isotopes analysis. So it's at the end of the 90s, the mass spectrometry evolved, and now we can measure isotope ratios for elements that we couldn't measure before. And we are realizing that most of them bring an information on the trophic level. This is the case for calcium, magnesium, and zinc isotopes. And I personally work on zinc isotopes. And so I will give you an example of what we can see. So you see here the zinc isotope also expressed with the delta notation, and differences between carnivores that are here and grazers and browsers. So it's interesting because you could see a difference between animals living in forests and animals living in savannas with these zinc isotope ratios. And you have also an information on the trophic level because the herbivores are here with the most elevated values and the carnivores have the lowest values. And I recently studied different French populations from different time periods, and what I could see is that cereal-based diets have elevated zinc isotope ratios, and the population with meat consumption have the lowest ratios. So it looks we can interpret the diet of humans and then hominins. So I will finish here, insisting on the fact that yes, there's limits to the isotope studies, but they brought a lot to the understanding of the ecology of the first hominins, and also for the Neanderthals and the modern humans. And that, yes, there's limits, but we are now on a stage where we have new isotope techniques, like the compound-specific isotope analysis, the single amino acids I presented, and also these non-traditional isotope studies that could open up new perspective. And I think in the coming years, you will see potentially estimation of the trophic level of these first hominins, Australopithecus, and Paranthropus. So, yeah, thank you.